All right. Well, welcome back, folks. I'm glad to see that about half of you are watching the videos. Again, these videos are not required. I'm not asking you. I'm not making these videos do, but these videos are more informative for you. It covers chapter 9. Again, like I've mentioned in the videos already. When we come back from break, I would like to get started with chapter 10. So when we come back from break, I will, for those of you who have not seen these videos yet, I will ask you to watch them just to kind of get caught up to speed, get you the information you need to take the AP exam. But I am very happy to see that about half of you are taking advantage of these videos and watching them. Like I mentioned last week, if you have questions, please email me. I am checking my emails over the course of this break here. And if there's enough of you who would like to meet live to get your questions answered, then we'll email me. I'll make arrangements for a time that we can get together to meet, and that way then I can address some of your questions, some of your concerns about the AP exam, and also about the material that we're covering here. Okay. Like I said, please keep watching, and like I said, if you have questions, make sure you email me and get those questions answered. Okay. All right, so let's go ahead. Let's pick up where we left off with yesterday. We were talking about the different types of hybridization. Hybridization occurs at the atomic level, that atoms hybridize in order to interact with other atoms in molecules. When atoms are by themselves, they maintain their atomic orbitals, and we learned about atomic orbitals back in chapter 7, when we talked about the s orbitals, the p orbitals, d orbitals, and those are atomic orbitals. Those are the orbitals that the atoms have when they're all by themselves and they don't interact with other atoms at all. Okay? And now these interactions that result in hybridization occurs when these atoms share their electrons. Electrons move between two atoms. Therefore, we do not see hybridization occur with ionic compounds. Because remember, with ionic compounds, what happens is that the atoms give up electrons and they gain electrons. There is no sharing, so there's no need to change the way that their electrons behave around them as a result of that. However, with covalent compounds, like we have here with ethene, with covalent compounds, let me go back up a little bit. For methane, sorry. With covalent compounds are like methane, where the atoms share their electrons, the electrons move between the atoms. Then what happens is the atoms have to change in such a way that they can accommodate for that movement. And so the localized electron model stipulates then that the electrons shared, in this case, then between the carbon and the hydrogens, remain between each one of those hydrogens and the carbon in a localized manner. But these electrons move back and forth, and so therefore the atoms have to hybridize. Now, the good news here for us is that hydrogen really doesn't undergo hybridization. So hydrogen remains in its s orbital state. So remember, and what you'll need to make sure you keep in mind as we move forward is to differentiate between atomic orbitals. Okay, so what these atomic orbitals are, okay, we have atomic orbitals. Okay. So the atomic orbitals versus the hybrid orbitals. Okay, and so what we will make sure we do is that you got to make sure you keep this in mind. So the atomic orbitals are the s, the p, the d, the f orbitals that we talked about back in chapter 7. So make sure you review this back in chapter 7. And the hybrid orbitals are orbitals that occur with the molecules. So these are molecular, these are atomic, and these are the ones we've learned about so far is the sp3, in which the atom takes the s and 3p orbitals and hybridize them together. Okay? And in forming these hybrid orbitals, you get then a different shape for these orbitals as opposed to the s and the p here. Okay? And you also get then a different arrangement in terms of their energies. Okay? And so this is what we are covering in chapter 9 here. We're talking about hybrid orbitals here. And so make sure you keep this in mind then that these orbitals occur within the atom. Okay, these orbitals here, and we're going to talk about then sp2, sp, d, sp3, and D2 sp3. And we'll talk about these here, with these here being that I'll just cover them, but you really won't need to know about their shapes and the electron configuration, the electron geometry associated with these two here. But you do need to know for these three here, and we'll talk about. Okay, but these occur within the molecule. Okay? And so this summarizes here for us the difference between atomic orbitals and molecular orbitals. And I think students new to this really get confused by this. And so I want to make sure you understand here that the difference lies with the orbitals that lie within the atom and the orbitals that lie within the molecule. But just like, but since these are both orbitals, both of these represent an electron distribution around, in this case, with atomic orbitals around the atom, the electron distribution in this case with the molecule, electrons between the atoms within a molecule. Okay, and so if you can keep this in mind, the difference then between atomic orbitals, electron and molecular and hybrid orbitals, it makes it very easy. It makes it easier for you to kind of follow what we're doing as we move forward. Okay. All right, so hopefully you have that summation. Let's go ahead then and let's talk about then what these orbitals are, okay, and how they interact with one another. So we saw then that with the carbon here, and I'm just going to draw this to the side here. There are going to be 4 sp3 hybrid orbitals that form, and the hybrid orbitals kind of look like a flower petal. You kind of imagine that the shape of these orbitals are the flower petals, and we saw then that with these orbitals, they are all degenerate, which means then the electrons then can spread out across these 4 orbitals here, which is where we get then the Lewis dot structure that I pointed out to you with carbon, where the 2 pairs then spread out. Okay, so you have 4 unpaired electrons rather than 2 unpaired electrons and 1 electron pair. Okay, so these are the sp3 hybrid orbitals, and if you notice, then you will form 3 sp3 hybrid orbitals, which then allows us to talk about conservation of these orbitals as well. Okay. All right, so with that said, then what happens here? Okay. The hydrogen then comes in. The hydrogen comes in with its 1 electron in the s orbital. So this is in its 1s orbital. And then what we're going to see then, and as it moves in, what we see then is there's going to be an overlap between the hydrogen 1s orbital. And so we'll draw this here. This is 1s. Hydrogen comes in with its 1s orbital. Hydrogen comes in with its 1s orbital. And so the overlap then occurs. Overlap then is between this overlap here, when it moves in, this overlap here is going to be between a 1s atomic orbital from hydrogen and an sp3 hybrid orbital from carbon. And this overlap here is what forms the single bond that we see right here. And that single bond then is the sharing of these 2 electrons here in each one of these bonds here. So you got each electron, 1 electron coming from carbon, 1 electron coming from hydrogen, and there you form then the single covalent bond for carbon and these hydrogen. Okay. This overlap here, this interaction, this is the bonding interaction that keeps the hydrogen and the carbon connected together. Okay. This bonding interaction we'll talk about much more in just a moment is what we refer to as the sigma bond. Okay. The sigma bonding interaction. And the sigma bond here is simply then the way that the orbitals overlap. Okay, the way that these orbitals overlap, and we'll talk about these more, but the way that they overlap then, the way that they interact with one another, okay, is basically one in which you can draw a line right through and they fall, and the orbitals fall within a line. Okay, so this sigma bonding interaction is a way in which the orbitals interact with one another. So we're going to see that in just a moment that there are 2 types of interactions, one being sigma bonding and another one being pi bonding, and we'll talk about that in just a moment. Okay. Okay. Let's continue on then, and let's talk about Okay, and so I asked you to take a look at this molecule here, which is ethene. And I asked you to draw the Lewis dot structure for this to finish out with yesterday. And so let's go ahead and draw the structure for it. So we have the formula here for ethene. Okay? And so I think we've done this before, and I'm just going to go ahead and draw this for you using the lines. Okay, we know that there has to be a double bond between carbon, the two carbons, and therefore there will be a single bond between the carbons and each of the hydrogens. Okay, so that would be the structure for the for ethene. Okay, and so let's go ahead and real quick. Let's describe the shape. Okay, and in order to do that, we have to describe the electron domains. Count the electron domains around each carbon. Okay, and so with electron domains around each carbon, then you have one. Okay, this is a region of electrons here. Even though this is a double bond, this counts as one electron domain. 2, 3. So you have then 3 bonding domains. Now, obviously, the bonding is different, but but we count this as one region of electron around this carbon here. Okay, so we have 3 bonding domains and 0 non-bonding domains. Okay. And based on this, and based upon what we did with VSEPR, then, whenever you have 3 bonding domains, remember the electron geometry then is going to be the trigonal planar. It's going to be trigonal planar electron geometry. And since we have no lone pairs, then the molecular geometry and the electron geometry will be the same. So therefore the molecular geometry, which takes into account the arrangement of the atoms around the center atom, around this center atom here, will also be the same as the electron geometry, which takes into account the arrangement of the electrons around that center atom. Okay, so make sure you remember the difference between electron geometry and molecular geometry as well. Okay, and remember the reason why again they are the same is because in this case then we only have the electron domains are all bonding. Okay, so make sure you keep that in mind. So with that said, then the angle between the bonds and if it assumes a trigonal planar geometry, the bond angle then the bond angle is going to be 120 degrees. Okay? 120 degrees between the bonds. Okay? So I think we all can agree on that one. And if you need to, make sure you go back and you use the FitLab to help you with this, okay? In order to remember how this works. Okay, so use the FitLab to help you, and then what we'll do then is if you have any questions, make sure you come by and you see. Okay. All right, so with that said, then we got the trigonal planar around each carbon, okay, with the bond angle then of 120 degrees. So if we take a look at the structure here in a greater detail, okay, what we're going to see then is that we have the bond length here. Okay, so let's go ahead and take a look at this. Okay, so if this is the some of the characteristics of the ethene molecule, and I give you the bond length here. The length here is about 108. The angle here is about 120. Okay, this is a little bit off here, but let's go ahead and let's answer this question here. Okay, so the question then is, why is it that so we have sp3 hybridization? Okay, so why can't sp3 hybridization account then for the hybridization of the carbon here and the interaction here? Okay. Between carbon and the carbon and the hydrogen. Okay, so let's go ahead and let's take a look at this, and I'm just going to answer this question for you. Okay. All right. So with that said, then remember with methane, when we saw methane. Okay, methane. When we talked about methane here, and I'll just draw it on this side, we said that carbon is sp3 hybridized. Okay? sp3 hybridization results in 3 sp3 hybrid orbitals around the carbon here, and the resulting bond angle of 109 degrees. 109 degrees here. Now, the angle here is going to be important for us, and that thus the geometry is going to be important for us to help us explain this. Okay, so with the bond angle here, this is tetrahedral. We first of all see that the ethene molecule is not tetrahedral. So therefore, it cannot have the same type of hybridization as the carbon. If the carbon here is sp3 hybridized, then it assumes the tetrahedral configuration. The 4 sp3 hybrid orbitals will assume that tetrahedron. Okay, so this is tetrahedral. Okay. And so based upon the bond angle, then we can assume then that this here is not going to be sp3 hybridized, because this is not going to be tetrahedral. We already saw then that the configuration here, the electron geometry here is trigonal planar. So based upon this, we can see then that we will not have that happening. Okay, and so what type of hybridization does occur here when we have this? Well, the hybridization then, and let me go ahead and close this out real quickly, is what we call sp2 hybridization. If sp3 hybridization involves one s orbital and all three p orbitals, okay, then sp2 hybridization then it's going to take, so with sp3, you take one s orbital plus the three p orbitals that we have here to form four sp3 hybrid orbitals. Okay. With sp2 hybridization, then you're going to take the s orbital and two of the p orbitals to form three sp2 hybrid orbitals plus one unhybridized p orbital right there. Okay, so if we start out with four atomic orbitals, we should end up with four orbitals in the end. Okay, so in this case, then we will have three hybrid orbitals and one unhybridized atomic orbital here. So one of the p orbitals will not be used. Okay, all right. So with that said, then the symbol and the name of the hybrid orbitals tells you then how it hybridizes. So sp2, it takes the one s orbital and takes two p orbitals and hybridizes them together to form a shape very much like what we saw with sp3. Okay, but you only have three of these hybrid orbitals instead of four of them, and one of the atomic orbitals stays unhybridized. Okay, and so if you can imagine this, then all of the sp2 hybrid orbitals will fall within a plane with one another here, and with the p orbital, then the remaining unhybridized p orbital, it will fall above the plane of the molecule, above the plane of those orbitals. Okay, all right. So you can imagine this here. So there it is. You have then the sp. You have then your sp2 hybrid orbitals following all on this plane here. Okay, and so this is accounts then for the angle between these orbitals, then will be about 120, and this will account then for the trigonal planar geometry that we saw occur with the ethene molecule. Okay? And so with that said, then the one unhybridized p orbital will fall above and below the plane of this above and below the plane of these hybridized orbitals here. So there you have your three sp2 hybrid orbitals and your one unhybridized p orbital. Now, it really doesn't matter whether these p orbitals are the x orbitals, the y, or the z p orbitals. What will happen is the unhybridized p orbital will just again fall above and below the plane the hybrid orbitals themselves. Okay. Okay. Right. This happens to achieve, the reason why this happens is that you achieve the maximum separation between these electrons that occupy these orbitals here, whether they are the molecular orbitals here, these hybridized orbitals, or the unhybridized atomic orbitals here. So remember, this is your atomic orbital, and these are your hybrid orbitals here. Okay, and I'll put here as a slash, and make sure you keep in mind that these occur in molecules, so we can also refer to these as the molecular orbitals. If these are your atomic orbitals, these will be your molecular orbitals here. Okay, and if you'll notice then, what you'll see then with these, okay, is that the three sp2 hybrid orbitals will then be all degenerate. They will fall in the same line. And so with the carbon then, what you can imagine then is that three of these will fall in, okay, and they'll spread out, and you'll have one that's going to be higher in energy than the other one. Okay, so going back to the previous slide, and I just want to do this really quickly. Going back to the previous slide, what you're going to notice then here is this. Okay, if this is your carbon atom here, this is your carbon atom here, you're going to see then that three of these electrons are going to fall, one each, into the hybrid orbitals there, and then you'll have the last remaining electron fall into the p orbitals, and this last remaining electron can either be on the top lobe here or the bottom lobe here. It could shift where it sits, we don't know, but it'll move between these two lobes of the p orbital here. Okay, so that accounts then for the four electrons of the carbon atom. Okay, All right, which means then the one electron here, and so let me just point this out to you then. The one electron that sits here in the unhybridized p orbital is going to be higher in energy. That means it's going to be higher in energy, and so it will bond differently. When it does bond, it will bond differently than these three here. Okay, so make sure you keep that in mind, because the question that we'll need to answer then is, how does it interact? How does it interact with the other atoms when this carbon here does hybridize? Okay, so let's go ahead and let's take a look at that. Let's take a look at how that bonds. Okay, so how do the atoms of ethene, how do they interact with one another? Okay. So let's go ahead and let's take a look at that. Now, if we saw then with sigma bonding, we saw then that, and we can do this again here, and I'll point this out to you, okay, that the interaction here between the carbon, I'll just let's draw this out here. Okay, so each carbon here will have an sp2 hybrid orbital, okay, sitting, okay, and we have another carbon here, okay, doing the same thing. And those are your three sp2. So this is sp2 hybrid orbitals. This is an sp2 hybrid orbitals. And this is sp2. So there are your three sp2 hybrid orbitals. Okay. All right. So in each one of these spaces here, then you're going to have the electrons. So you have 1, 2, 3 electrons there. For this carbon here, 1, 2, 3 electrons here. All right, and so with that said, then you have, and I'm just going to draw this in a slightly different color so that we can differentiate here. Remember, with the sp3 hybridization, you're going to have one atomic orbital. So you can imagine there is the p orbital there, and this is so this is your plane right here. So therefore, you have another p orbital. So this is a p orbital that is unhybridized. Okay. And you'll have your one electron in there, and you'll have the same thing here. This atomic orbital, so this is another p orbital here, okay, as well. And so with that said, then the last remaining electron is going to fall in there and there. And again, these two could be down here as well. I'm just going to draw them on the upper lobe here just for the sake of for the time. Okay. All right, so then with the hydrogen here, so let's go ahead and draw this interaction here. The hydrogen comes in. Hydrogen then comes in with its one electron, and this one's going to be in the s orbital. Okay, so the hydrogen here is an s orbital, unhybridized, s atomic orbital. And the same thing holds true. And so we said then with this particular case, this was a sigma bond. Okay, so let's write this down. So this interaction here, okay, this interaction here is a sigma bonding interaction. We already saw that. Sigma bonding interaction, which we just refer to as a sigma bond with the Greek letter sigma bond, indicate the interaction there. And so that holds true then for the hydrogen here, here, and here. Okay. So if you take a look at this particular interaction here, you're going to see then that these two hybridized orbitals here, they actually, when they overlap, and that forms one of the bonds here, when they overlap in a manner where you can draw a straight line through them, which means then that this interaction here is a sigma interaction as well. This is going to be a sigma bonding interaction as well. That means then one of the bonds here of that double bond, and I'm just going to arbitrarily choose this bottom one here, is a sigma bond. Okay, so this is a sigma bond. This is a sigma bond. This is a sigma. So all the bonds between the carbon and the hydrogens will be sigma bonds. This double bond here, one bond of that double bond will be the sigma interaction here. That means these two electrons will flow across these two hybrid orbitals here. So the interaction between the hybrid orbitals forms a sigma bond here, because you can draw, again, a straight line basically through the interaction there, and you can do the same thing here, and that's what accounts for the sigma bonding interaction here. Okay. The second of the two bonds here This is what we refer to as a pi bond, and I'm running out of time here. So what I'll do is we'll talk about this tomorrow. But this interaction here is a side-by-side interaction. You can imagine that these two pi bonds, so the sigma bonds fall within a line like this. The two pi bonds they are lined up side by side with one another instead of falling along a line. So we refer to that as a pi bonding interaction. Okay. And so what we're going to do tomorrow then, and what I'd like to do is try the homework for tonight. What we're going to do tomorrow is we're going to talk about these interactions and explain then how these interactions account for the types of bonds that form between atoms. And so we'll continue with this discussion of these hybrid orbitals, but we're going to add to that then how these hybrid orbitals and how the orbitals interact with one another. So we're going to talk about these interactions here, how they interact with one another to form these bonds. So the atoms first have to form the hybrid orbitals, they'll hybridize, and then they have to interact with the other atoms of the molecule to form the bond. And so when we talk about sigma bonding, when we talk about pi bonding, we're talking about the interactions between two atoms, and we'll go ahead and continue that tomorrow. Okay. All right, so please keep watching the videos. And like I said, if you have any questions, email me. And if we have to, I'll arrange a time that we can meet. I'll do office hours again. And that way, then I can answer your questions live. Okay. All right, so we'll continue this discussion tomorrow, folks. And I will we'll continue with it at that.